All right, winding down, we've got 3 more pages of the review guide to go. All right, so Lewis dot structures. What the questions you see on the test will be is they will give you the Lewis structure, and they'll ask you to identify the correct one or the incorrect one, or what is the shape of this particular molecule. Okay. So remember what we do. I'm going all wonky. Focus, focus. Uh-oh. Come on. Well, all right, there we go. Okay, Lewis structures. Remember what you've got to look at. You have to know the number of valence electrons. So, for example, carbon has 4 valence electrons. Each fluorine has 7. So that tells us that we have, 7 times 4 is 28, plus 4 for carbon is 32. All right, so remember you put the middle atom in, and you put the other atoms around it. And then you connect those with a single bond. All right, and then you put 8, make it so that each fluorine has 8 valence electrons around it, like so. Okay. So if you look at this, all right, now we have to count how many electrons we've used. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So this structure is done. Okay, we have the right number of electrons. Let me see if I have the shapes. Let's see. All right. So this is what you will get, and I will print this out and give it to you on the test, for the test. Okay. And remember, what you have to do is you have to look at the number of number of elements attached, and then if there are any lone pairs of electrons on the central atom. So for CH4, we had a central atom, and then we had 4 atoms attached, no lone pairs. So that tells us that this shape is going to be tetrahedral. And I am including the shapes on this review guide that you will see on the test. So if you don't see it here, you won't see it on the final. So tetrahedral. All right. NH3. So nitrogen has 5 valence electrons. Hydrogen has 1 each, so that's a total of 8 valence electrons. So we do the same thing. We put nitrogen in the middle. We connect the 3 hydrogens with single bonds. We give whoops, oh goodness gracious, that was almost a big mistake. Hydrogen doesn't need 8 electrons, remember? So I got all carried away. Hydrogen is satisfied with just this single bond because that gives hydrogen 2 electrons. So let's see, we've used 2, 4, 6. We have 2 left over, which is amazing because we need 2 more on the nitrogen so that the nitrogen has 8 valence electrons. Okay, so this molecule has 3 atoms attached and 1 pair of electrons. So let's hop over here to our shape sheet. So we have, let's see, and remember we have numbers of electron domains. So this still has 4 electron domains, but it's got 1, 2, 3 atoms attached and 1 lone pair. So trigonal pyramid is going to be the shape of NH3. All right, carbon dioxide. Carbon has 4 valence electrons. Each oxygen has 6, so that's 12. So we've got 16 electrons. So central atom attached to the outer atoms give each outer atom 8 electrons. Okay, now let's count and see what we've got. 2, 4, 6, 8, 10, 12, 14, 16. Now, so we've used up all of our electrons, but notice that carbon does not have an octet. What that means is that we are going to take this pair of electrons off and put them in there and make a double bond. And we're going to do that on the other side too and make a double bond. Okay, so now if we count, we've got 2, 4, 6, 8, 10, 12, 14, 16, which is the number of electrons we have. Now, this one also has a little trick to it because in terms of electron domains, we only have 1, 2. Even though it's a double bond, it counts as just 1 electron domain. So if we look over here, 2 electron domains, there's only one option. It's going to be a linear molecule. So let me go back over here. So this shape is going to be linear. Linear. Okay. H2O. Oxygen has 6 electrons, valence electrons. Hydrogen has 1, so there are 2 hydrogens. So we have a total of 8 electrons here. Oxygen's in the middle. Hydrogens are on the outside. Hydrogens don't need 8 electrons around them. So we've used 2, 4. We've got extra electrons, so we can put 2 here and 2 here. Okay, so now we've used 2, 4, 6, 8. We've used all 8 of our electrons. This molecule has 1, 2, 3, 4 electron domains. So if I hop back over here to my shape sheet, 4 electron domains, but it has 2 atoms attached and 2 lone pairs. So that is going to be a bent molecule. All right, so bent. All right. Okay, next we have electronegativity. Remember when we talk about bond polarity, we have polar, nonpolar, and ionic. Okay, and you'll have this table that shows you the polarities of different atoms. What we need to know is if something has a difference, electronegativity difference. So En, electronegativity difference, less than 0.5 is going to be nonpolar. Greater than or equal to 1.9 is going to be ionic. And then between 0.5 and 1.9, that is going to be a polar bond. Okay, so all you got to do for these is look at the values. So carbon is 2.5, oxygen is 3.5. The difference is 1. So that makes this a polar covalent bond. Lithium and fluorine. Lithium has an electronegativity of 1. Fluorine has a electronegativity of 4. So the difference is 3. Huge difference. So this is an ionic bond. Carbon and hydrogen. Carbon is 2.5. Hydrogen is 2.1. So a difference of 0.4. So this is a nonpolar bond, nonpolar covalent. And last example, nitrogen is 3, hydrogen is 2.1. That gives us a difference of 0.9. 0.9 is right there in that range for a polar covalent bond. Okay, those should be pretty easy for you to figure out. All right, how many valence electrons? This should be hopefully easy too. You look at the group number on the periodic table. Oxygen is in group 16, so it has 6 valence electrons. Magnesium is in group 2, so it has 2 valence electrons. Chlorine in group 17, 7 valence electrons. Sodium in group 1, 1 valence electron. Boron in group 13, so 3 valence electrons. Neon is in group 18, so it's got 8 valence electrons. Phosphorus is in group 15, so 5 valence electrons. And silicon in group 14 has 4 valence electrons. Okay, hopefully these are the things we've been using, and hopefully these things kind of stuck, and these are going to be easy, quick questions for you to answer. How many bonds will each of the atoms form? Okay, so if you recall the way we figured this out, so oxygen had 6 valence electrons, right? 1, 2, 3, 4, 5, 6. So an atom can form as many bonds as it has solo electrons. So oxygen is going to form two bonds. Chlorine has 7 valence electrons. So it's only got 1 solo electron, so chlorine will make 1 bond. Boron has 3 valence electrons. Boron's special. Remember, boron is content with only 6 electrons. It doesn't need 8. So boron is going to make 3 bonds. Argon. Argon is a noble gas. Group 18, 8 valence electrons. So argon is a noble gas. It is not going to make bonds. Nitrogen, group 15, 5 valence electrons. So 3 solo electrons, it will form 3 bonds. Carbon, group 14, 4 valence electrons, it will form 4 bonds. Okay, I feel like we saved the easy stuff for the end. We'll see. Oh, maybe I spoke too soon. Maybe not. Let's look. Okay, so these give you Lewis dot structures, and we ask 3 questions. Are they polar or nonpolar? What type of IMFs do they have, intermolecular forces, and what is their shape? Okay, so remember, for something to be polar, one of 2 things has to be true. It either has to have a lone pair of electrons on its central atom, so this is polar. This has a lone pair of electrons on its central atom, so this is polar. These 4 do not have valence or electrons on the central atom. So we have to ask another question. That other question is everything attached to the central atom the same? Okay, so in this case, we have 4 hydrogens attached. So this is a non-polar compound. Carbon dioxide has 2 oxygens attached. Same thing, non-polar. We already said H2O is polar. Boron trifluoride, 3 of the same atoms attached, non-polar. And finally, this carbon has oxygen and 2 hydrogens attached. So that is a polar bond because the atoms attached are different. Okay, now, intermolecular forces. Remember, we have London dispersion forces, LDF, dipole-dipole, and hydrogen bonding. Okay, remember, every single compound that we look at has LDF. Okay, Now, nonpolar molecules, the only force they have is LDF. All right. So carbon tetrahydride only has a London dispersion. Carbon dioxide, only London dispersion. Boron trifluoride, only London dispersion. Okay. Our polar molecules, all polar molecules have dipole-dipole. Okay. And then hydrogen bonding is that special situation where we have a hydrogen connected to an oxygen, a hydrogen connected to a fluorine, or a hydrogen connected to a nitrogen. Okay, so this molecule has hydrogen bonding, and it is the only one. Okay, and then the strongest intermolecular force is hydrogen bonding. The weakest intermolecular force is London dispersion forces. Okay, and then shapes. I'm going to not go jump back and forth, but if I look at this CH4, 4 electron domains, they're all atoms attached. The shape here is going to be tetrahedral. Carbon dioxide, we did that one on the other page, linear. And if you have questions about these, just shoot me an email or we come into class and we can talk about it. Water, we said was bent. We already did some of these. Boron trifluoride. This has 3 electron domains. All of them are atoms, no lone pairs of electrons. So this is a trigonal planar shape. Okay. NF3, 4 electron domains, 3 atoms, 1 lone pair. This is trigonal pyramid. And then carbon with the oxygen, 2 hydrogens, 3 electron domains, all atoms. So this is also trigonal planar. Okay. And this is something we talked about briefly in class. And you'll see pictures like this. Okay, so it's asking us, do we have strong acids or weak acids? And are they concentrated or dilute? Okay, so strong acids, and this is what we said in class, strong acids break apart into their ions. So like if we had like HF, okay, it would break apart into hydrogen and fluorine. So we would have it all broken down, okay? So if you look, this shows that all of the pieces are separated from each other. They're all ionized and dissolved, okay? So this is a strong acid. And just to make sure you remember this, we have used H plus as our acid. Some things, the test that you're going to see, may also use H3O plus to represent an acid. So for HF, you would have H3O plus and F minus, okay? If it was completely dissociated, it's going to be a strong acid. Look, this one's completely dissociated, so this is a strong acid. The individual ions are separate from each other. If you look at this one, you can see that some of the molecules are still connected, and then there are some that are dissociated. That makes this a weak acid. Same thing here. We have some that are in the form of molecules, and then we have some that have dissociated into ions. So this is also a weak acid. And then strong versus dilute, or excuse me, concentrated versus dilute. Concentrated atoms or concentrated solutions are going to have a lot of solute particles. Okay, so more particles in the solvent. So if you look, this is going to be concentrated. This is going to be dilute. This is going to be concentrated. This is going to be dilute. Okay, so when you look at these on the test, when you see this, you'll probably see things like this to represent an acid, and some of them, if it asks you, hint hint, it's talking about acids, it's going to ask you about an acid. If you see something like this floating around, something like this is a base. Whoops, you can't see it because I wrote it here. So if you see something with a hydroxide, that's a base. So don't, it's going to ask you for an acid. The acid is either going to have H3O plus or H plus. All right. Okay. Which of the following would speed up the rate of a chemical reaction? Stirring. Yes. You stir it, it's going to mix faster. Cooling the reaction? No. Breaking the substance into smaller pieces, that's increasing the surface area, that gives more surface for the solvent to get around, so yes. Increasing the concentration of the reactants, that will speed it up because they'll be able to come into contact with each other faster. Heating the mixture, yes. Adding a catalyst increases the rate of a chemical reaction. Increasing the surface area, and then increasing the volume of a container, that just is saying you're putting it into something bigger. So no, that is not going to have an impact on the how fast something dissolves. All right, pH, pOH. All right, so pH, we have pOH is 10. What is pH? Here's what you've got to know. pOH plus pH equals 14. So pH is going to be 4. Okay. This gives us H3O, that's acid, so that would be the same as this. Hydrogen ion concentration is 2.5 times 10 to the negative 6th. What is pH? Remember, pH is equal to the negative log of hydrogen ion concentration. So let me get my calculator back out here. So this would be negative log, whoops, okay. I got to do it on my calculator's terms. So 2.5 times 10 to the negative 6. And then it's the negative log of that. So if I do log and I do negative, the pH is going to be 5.6. Okay. Let's see, hydroxide ion concentration. It gives us hydroxide ion concentration. It asks us the pH. So there are multiple ways to go about this. I think that I would just do the same type of calculation here to figure out pOH. pOH is going to be the negative log of hydroxide ion concentration. So if I plug this into my calculator, 3.9 times 10 to the negative 8th. Okay, I want to do the log of that and the negative log. So this tells me pOH is 7.4. Then I know that pH plus pOH equals 14. So if I do 7.4 minus 14, it is 6.59. So I'm going to say 6.6 would be the pH. Okay. Oh, check it out. We're on the last page. Woohoo! All right. It's asking us to calculate the hydrogen ion concentration for the following. Okay. So if the pH is 9.2, what is the hydrogen ion concentration? So for this, hydrogen ion concentration, and again, we use this. Hydrogen ion concentration is equal to the negative log, nope, is equal to 10 raised to the negative pH. Okay, so let's see if I can do that. So this would be 9.2 as the pH, so I would do 10 to the power of negative, oh, that didn't work, 9.2 and the negative, there we go. So my calculator, and make sure, maybe we can check on this, I would say maybe Monday, let's make sure you know how to do these on your calculator that you're going to use on the test. I didn't bring a school calculator home with me, but so I have to type in the pH first. So pH is 9.2, it's negative, and then I want 10 to raise to that power. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 6.3 times 10 to the negative 10th. Is that what I said? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, 6.3 times 10 to the negative 10th. And that is a molarity. Okay, pH and pOH don't have units. Hydrogen ion concentration, hydroxide ion concentration have units of molarity. All right. So let's see, pOH of 10.8. So let's see, I can do pOH plus pH is 14. So 14 minus 10.8. So this has a pH of 3.2. So I'm going to do the same thing. I'm going to do 10 raised to the negative pH. So negative 3.2 is 1, 2, 3, 6.3 times 10 to the negative 4. Okay. Last one. Hydroxide ion concentration is this. What is the hydrogen ion concentration? This one I'm going to use this. Hydroxide ion concentration times hydrogen ion concentration is equal to 1 times 10 to the negative 14th. So I can do 1 times 10 to the negative 14 divided by 3 times 10 to the negative second. And I get 3.3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times 10 to the negative 13. Okay, so those should be fresh because we just did that titration. Okay, this is a question you're going to see. Here's what you got to remember. The stronger acids have a higher equilibrium constant. Okay, these were the equilibrium constants that we did in our solutions issue, unit, I mean, and realistically, you could calculate these. I would rather you just not take the time to calculate them. That's why we didn't talk about it. But the larger Ka is the stronger acid. So 4.1 times 10 to the negative second would be the biggest, the largest number. Remember the negative exponents put a lot of zeros in front. So the one with fewer zeros in front is what I'm looking for. All right. And, oh, some easy-ish things. Types of reactions. All right. Two elements combined to form one compound is synthesis. Silver nitrate plus, so two compounds react to form two compounds. They switch. That is a double replacement. A hydrocarbon plus oxygen, that is combustion. A compound that breaks down into two elements, that is a decomposition. a compound, the metals switch places. That is a single replacement. All right. Let's see. In the following reaction, would the change described cause the equilibrium? So this is Le Chatelier. Okay, remember the teeter-totter. So if we add hydrogen, it's going to shift right towards the products. If we add water, it's going to shift left. If we cool the reaction, okay, since heat is on this side, if we cool it, we would need to shift right. Removing H2O would also shift right. Adding heat. Adding heat would make us shift left. And removing oxygen would have us shift left. And this is a question that we did not talk about resonance structures because they're very complicated. Here's what you should know for these questions. The number of resonance structures. Basically what it means is these bonds, whoops, you can't see them. I guess I should slide them up here. These bonds can switch places. Okay, so like I could take a pair of electrons here and make a bond there and take this bond away and add electrons. Here's what you need to know. Resonance structures. You can have as many resonance structures, resonance, as you have oxygens. So CO3, 3 resonance structures. SO4, 4 resonance structures. Okay. Another question that I kind of, if you can remember that, it's a gimme. If not, hopefully you'll be able to make an educated guess. And believe it or not, we are at the end. So this, I believe, is the last video that you will see before the final. I guess I'll look at that other little packet that I gave you with some random things in it. But I hope these videos help. I apologize that I did not get them done sooner, but hopefully if you got them in enough time to look at them and be prepared for this final as much as you possibly can. So let me find there we go. All right, that is it. This is Mrs. Lyons signing off. I hope you're having a wonderful weekend. I hope you have a wonderful summer. I'm going to miss you guys, so you'll have to come back and visit with me next year and tell me all the good things that are happening. All right, good night, good luck, take care.